My name is Farid Zidat. I am a technical specialist within Altair. I am happy to share this work we did together with my colleague Spiros, and we already presented in the conference PEDES India last year. So why we did this work? First, I like this machine, but this is a good use case as well for ROM AI. For reduced order model of induction machine, we can determine the parameters of this equivalent scheme by two classical tests, the no-load test and short circuit test, with simulation or with measurement. But unfortunately, this equivalent scheme has some limitation, especially for the maximum load and the starting point. Here we have a comparison of the torque given by the equivalent scheme and the torque measured or computed through a flag study at a high frequency, 100 hertz, and this voltage. For the same voltage but lower frequency, we can see the same comparison, and we can see clearly that uh, the equivalent model is really limited for if we need some accuracy. But the finite element computation can be also expensive, especially for variable speed and system analysis. This is another work we presented where we have a fixed frequency and a fixed voltage, but we can see clearly that to have an accurate model, the parameters of the equivalent scheme need to be fitted for each sleep value, which again can be a bit expensive in time computation. Another work we presented at ECCE 2023. Here we vary the frequency and the voltage, and we wanted to determine the parameters of the equivalent scheme. Here also, as you can see, the parameters are really variable according to the frequency and especially for the frequency and the voltage. Um, in the conclusion, if we want really to have accurate results from the equivalent circuit of the induction machine, so we need to fit the parameters according to the frequency, to the voltage, and the, the slip, so the load of the machine. And as you can understand, this is really expensive. So here the idea comes, why not to mix the reduced order model and with AI, and this is why it fits really good with our solution, ROM AI. So we can understand that these are also depending on some data, as explained by my colleague Spiros, and the the expense actually of this model belongs to the data, and we want here to use data, but not a lot of data. So the first thing we have to do is to determine the classical equivalent scheme through two tests, a no-load test and short circuit test. So then we use this initial test, and we want here to reduce the number of slip, the number of voltage, and the number of frequency we want to do. If we plot the torque versus slip, sorry, if we plot the torque max, the value of the maximum torque, and the corresponding slip versus frequency, we can see that it is very dependent on the frequency here for given voltage, of course. And if we plot now the value of the torque max and the corresponding slip max, we can see that this value of the torque is not is constant over the voltage variation, and we can see also that the slip corresponding slip is actually this is the value of the slip that will vary. So what we want to do here is to select few value of the voltage and then vary more the frequency. And for each couple of voltage and frequency, we are going to select only three values of slip. So no load test, no load slip, maximum slip, and the local rotor slip. And we are going to launch flash 2D computation for this combination. So we have a total of 360 finite element working point. For each working point, we are going to extract to compute the torque, the rotor joule losses, the stator current, the iron losses, and the reactive power. This is mainly what we need to make a power balance and compute the power factor. And we are going to use this data. So 360 working point are depending on the slip, the voltage, and the frequency. And then the training is done. The quality of the training is depending on this ratio R. Closer R is to 1, better is the training, the trained model we have. So we have this trained model, ROM model for each quantity, and then we are going to use it in Activate, to inactivate, sorry. We want to apply this. We trained the model on this machine, which is close to the Tesla machine, actually. It's a 60 slot, 74 bars, a 4-pole machine. So we computed 360 points on it. We trained ROM on this 360 points. Then to validate our ROM prediction, we want to compare it to some test results. So we computed 6,000 working points now in order to see how accurate will be our results. Something we did first, we used directly the data we trained the ROM on it, and actually using that we had a very bad result. So Spiros, my colleague, had an idea is to switch to logarithmic scale because for lower slip, a higher voltage, we have a very big torque, and in the reverse side we have very small torque. So we need to consider in both small and higher values, and switching to the logarithmic scale helped a lot to improve the accuracy of the prediction from our ROM model. Then what we did, we computed 6,000 working points through Flash2D, which are our references. We made the same, we predicted the same results through our ROM model. And as you can see on the screen, the comparison here, we selected only few values. So for the highest voltage and for the highest voltage, which is 260 volt, and the smallest voltage, which is almost 17 volt. And here you can see the variation of the quantities versus slip and versus frequency for these both voltage value. For the rotor joule losses, which is very sensitive actually to frequency and the voltage, we can see really a good agreement between the prediction from ROM AI and the reference, which are flux simulation. The torque also we have a really good agreement, and the stator current. Here we can see the maybe have a look on the mean relative error on the total 6,000 working point. We have here the maximum of almost 5% deviation, which is really very good, especially for the induction machine. Something I forgot to mention, if I want to come back here, on the 360 point for the training, we considered 80% of this value for the training. And in the training stage, we also dedicated 20% of this amount in order to test already our model before going to the validation. So yeah, in conclusion, we showed the interest of the single phase or the reduced order model for induction machine, which is very useful for system analysis, for instance, and speed variation. But unfortunately, this equivalent scheme can be very limited, especially for local rotor and the high or the maximum torque value. We showed this sensitivity to the frequency, the voltage, and the slip. We showed also this new approach and promising approach, mixing AI and the reduced order model. And this method is applied or was applied on a validation example through 6,000 working points. So the interest here is that ROM AI for 6,000 to predict 6,000 working point is almost instantaneous. Where to compute this 6,000 working points through finite element computation in my computer, 30 minutes were needed using parallelization, of course, right? When we started this work, the training took almost 30 minutes, but now with the recent version of ROM AI, the training is almost instantaneous as well. So here the speed up I show on the screen is about 10 times. But nowadays, with the current version of ROM AI, it can be almost 20 times as a speed up. That's it for me. Thank you very much for your attention, and I'm happy to answer the question if there are questions.